So, good question. Why don't we do one of these? So, let me make something up because I've not got anything planned. So, should be in my notes, but so let's have a look. Let's have a oh, you happen every time, and I don't really care. So we'll have that, and then so let's say 8 volts. Let's say 2 ohms. Let's say 5 farads. So questions I could ask. PD on resistor at t equals 0 seconds. I'm saying when the switch is closed. You know, you got to work with me on this. I don't want to be a lawyer and say, you know, an instant, but not too big an instant after the switch is closed, the switch allowing current to flow through wires that are made of metal, you know. I want to just say, you know, time t equals 0. So then I'd use my conceptual understanding. And I'd say, well, at time t equals 0, Q on the capacitor equals 0 coulombs, and delta V is equal to, charge is equal to, I can never remember this, Mike, capacitance is equal to Q over my delta V. So my delta V is equal to my Q over my capacitance. Q0 delta V equals 0 volts. And I kind of know that. Let's do it the really conceptual way. Time t equals 0, no charge on my capacitor because there's no time for the charge to get there, so no potential difference. There's no electric field. There's no nothing. Yeah, okay. Yeah, agreed?
Wait, so we just solved for the potential difference across the capacitor?
So this is my Q is 0 on the capacitor. Oh, yeah, sorry. Yeah. Need to continue my, that's the capacitor. You saved my bacon here. So therefore, my delta V across my resistor is equal to, well, whatever's left, 8 volts. I could have asked you, what's the charge on the capacitor? I could have asked you, what's the voltage across the capacitor? I could have asked you what the voltage on the resistor is. And the last little thing I can ask you is, I is equal to delta V resistor over R, which equals 8 over 2, which equals 4 amps. So those are those 4 little bits I can just get out of just this bit of conceptual understanding. And then PD resistor at long time. Yeah, long time. Okay. So I say, well, let's have a look. I'm going to go into this the different way now. I'm going to say, well, I is equal to 0 amps because I know no current flows. So I'm going to say, well, my potential difference across my resistor is equal to 0 volts because no voltage for no current. That's not obvious. That we tend to think of the voltage pushes the current through. And that's the EMF of your power supply pushes the current through. But the current flowing creates the potential difference. So it's, you know, V equals IR, but sometimes I equals V over R, where V is the potential difference. Yeah, you see, just a different kind of like mentality about it. So that means that my delta V across my capacitor equals 8 volts. So therefore using Q is equal to, C is equal to Q over delta V, which gives me that Q is equal to C delta V, which equals, 5 times 8, which equals 40. And what's the units for charge? Coulombs. Okay, so I got that guy, I got that guy, I got that guy, I got that guy. So, boom, 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 boom. Again, 4 things I can find out. Let's say that, so now here comes, there's another question I can ask. Time constant. What is my time constant? Tau is equal to RC, which equals 2 times 5, which equals 10 seconds. There's another thing I can ask you. Now, I got to do that question. I got to do that calculation when I'm setting this thing up, because I'm going to turn around and say, what's the charge on the capacitor at? And I'm going to say, I think I'm going to say 7 seconds. So I say, oh, charge on the capacitor when I'm charging. This is this is cap and this is charging. Charging the capacitor when I'm charging is equal to my Q max, 1 minus e to the minus t over tau, which equal, what is my Q max? Q max is equal to my EMF multiplied by my capacitance, 1 minus e to the minus t over RC. And that equals, and now I'm just doing sums. It's going to be 8 5 1 minus e to the minus t is, what did we say? 7 over, and then RC is going to be 2 times 5. So paper's cheap, so I'm not going to. I'm sorry?
Why your E is
I can't, what are you saying? I'm sorry.
why your E is A there?
Why my E is what?
A number.
Because it's 8 volts. EMF. Yeah, epsilon is E, which is. It's that curly E, yeah?
We're not talking about epsilon naught.
Oh, we're not talking about epsilon. Oh, I'm so sorry, no.
Yeah.
It's not epsilon naught. It is the symbol, the Greek symbol for EMF. They call it epsilon, yeah? As opposed to V. Just so you know. Oh, that's not a potential difference. That's an EMF. Okay? Oh, I'm sorry about that, yeah. That's a good question. 1 minus e to the minus 7 over 10, which equals 40, 1 minus e to the minus 0.7, and then we're doing calculator stuff, aren't we? Still important. So important, I'm going to put my glasses on. Still important. So we're going to go, and I like to do these backwards, so I'm going to go second e to the x, and then I go, oh, that's little negative 0.7 close bracket, and then I go 1 minus second answer bracket, and then I go times 40. I make fewer mistakes when I do it like that, and that equals, oh my word, 20.14 coulombs. Okay, if I asked you for delta V capacitor at 7 seconds, you'd simply say, oh, delta V is equal to Q over C, which equals 20.14 coulombs over 5, which equals 4.03 volts, which means you, pardon? I'm sorry? It doesn't matter. Okay, yeah, you're right. That doesn't matter. You remember that thing about if it's 5, one time you go up, one time you go down, one time you go up, one time you go down, so your life is evened out.
I'm pretty sure it's just lowers the rocket points.
But yeah,
Sir?
Yeah.
Why didn't you do the one with discharging? Why did you use the charge?
because I chose to do it charging.
Oh, you didn't ask for it.
Yeah, if I did the one that was discharging, then I would, you would have to then know, so for discharging, all right, let's do a discharging one. We got time? Yeah, we got
You
this.
could probably tell us, like, I flip a switch and, like, you find the time constant and you know, like, whether it's charging or discharging.
So I'd tell you it's charging up or whatever. I wouldn't keep that secret from you. But the, so for, let's get a small pen, yeah. So for discharging, you would basically open that switch and you would add that wire there. So you would know by the time that you discharged that that had 8 volts across it. So you know the voltage is 8. And the equation you would use down here would be the other one. Yeah. Yes?
And sir, how do you know that the current is equal to 0 times 8?
Where?
I is equal to 0. Yeah, that one.
There.
Yeah.
Oh, because this is when I'm first beginning, yeah? Sorry, this is after a long time. And once you've had a long time, you're charged up.
Oh.
So no current is flowing once you're charged up. No traffic flows into your parking lot when it's full. It's jam-packed. It's a traffic jam, so no one's going anywhere. So from intuitively, from conceptual stuff, okay? Cool. I'll stop that there.